A sequence is a function, so just like a linear function, but its domain is the set of positive integers. So you can't have term 1.5. Term is just the ordered list of the numbers. You can't have a 1.5, or you can't have a -7. So a sequence, think of it as like the months of the year, right? You can't have a negative month. You can't have a partial month. So a sequence just has a domain of the set of positive integers. And it just is represented by listing the values in order, just like that warm-up that we did, right? All of these are sequences. This would be called term 1, 2, 3, 4, 5, and you had to find term 6. Same here, term 1, 2, 3, 4, 5, you found term 6. I guess on each of these you were finding the 6th term. So there's special notation on how to designate what term you're on, which we kind of get into the notation down here, a sub n. If I wanted the 6th term, I would be at a sub 6 or a sub 10. It's going to be important when we talk about series if you have an infinite or finite sequence. Infinite just goes on forever, finite ends. So if I wanted to give you an example, infinite, 2, 4, 6, 8, dot, dot, dot. That can go on forever and ever and ever, right? Just add 2 every time. That would be infinite. Finite might be 2, 4, 6, 8, and then a bracket showing you that you've ended. Doesn't really matter talking about sequences, but when we start talking about a series is when you add up the terms of the sequence. I cannot add these if it's going on forever, but I could add these 4 terms together, right? And I would get 20. So you can add a finite, but you can't add an infinite series. There's going to be an exception to that, but most of the time you can't add it if it's infinite. And then I talked a little bit about in our warm-up, closed versus recursive. If I know the recursive pattern and I just know that I'm adding 2 and then I'm adding 3 and then I'm adding 4, I can't generate the 10th term of this, right? I would have to keep, adding 5, adding 6, adding 7, adding 8. That's recursive. But on like this one, I knew this was 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. I already know that the 15th term is just 15 squared. That would be a closed formula because I could think about what I would plug in to just get that one term. So we're gonna learn how to do closed versus recursive, and you would have learned this normally in Algebra 2, but we're kind of starting fresh with sequences because most people in Algebra 2 skipped this unit. So I'm just kind of laying out there some definitions that some of you might have heard, but most of you probably haven't heard. A sub n notation. So you could have function notation that you're familiar with, right? F of x equals 3x minus 2. That just has a domain of all real numbers. I could plug in 1.5. I could plug in -10. But if it's written in sequence notation a sub n, that's like telling your brain you're not allowed to plug in 1.5 anymore. And if you notice on your calculator, I never put mine in sequence mode personally, but if you go to the mode key, one of the choices, where is it? Do you see function, parametric, polar, or do you see how there's a choice for SEQ, sequence? I'm just going to put mine into sequence mode just to show you. If I go to the y equals menu, it's U of n, meaning it's a sequence. So it changes your y equals menu kind of into sequence mode. I'm going to go back to mode though, and I'm going to put it back into function mode. Okay, so then you're back to like y equals. So anyway, sequence notation is completely different than function notation. That's the only way you would know that you're a sequence instead of a function. And then when you graph terms of a sequence, your points are discrete, meaning they're not connected. So the way I think of this is if you're renting an apartment, you usually pay rent by the month, right? So you pay 1 month's rent, then you pay 2 months rent, then you pay 3 months rent. You never pay month 2.5 right? So if you're paying $1,000 a month, you're never going to pay $2,500. You're going to pay 1,000, then 2,000, then 3,000, right? So you've never paid $2,500 in rent. So you would not connect the points like a straight line because those other points are really not defined. You would just hit a dot, and a dot. So when we go down here and graph them, we're just going to remember that we don't connect the points. So we're just going to look at a bunch of examples, and this is what's on homework 5-1 when you come back from break. So in your book, one thing that you might need to do is just generate the 4 terms of the sequence, which is like generating a function. Plug in 1 and see what you get. So if you plug in 1 for n, so what I usually do is I know I'm going to list the first 4 terms of the sequence. So to find term number 1, I'm going to plug in 1 in the original sequence. So I would get what? -1 to the first power is still -1. And then 2 times 1 is 2. Minus 1 would be 1. So I've got -1 in the numerator, and you could write this out, right? -1 in the numerator, +1 in the denominator is -1 as my first term in this sequence. So now let's plug in 2 and see what we get. Now you're squaring a -1 in parentheses. So that's going to become +1 in the numerator. And in the denominator, you're going to get 3 because you get 4 minus 1. So we're going to get +1 over 3. So -1 and then 1/3. All right, so you plug in the number 3, see what you get, and you plug in the number 4 and see what you get. So you're generating the terms of a sequence. You could also plug it into your y equals and just go to your table, right? And see what, when x is 3, what do you get? And when x is 4, what do you get? So totally different than our last unit, or really anything we've done this year besides kind of thinking about functions. So let's see, this one, when you plug it in, you get a negative back in the numerator, and then this would be 6 minus 1 is 5. So now we're at -1/5, and then you can start to see the pattern. I know that I'm going to be positive, and I'm going to be 1/7, right? See how now you can see the denominators are 1, 3, 5, 7. So when you plug in 4, you do get 7 in the denominator, so 1/7. So sometimes once you start generating the pattern, you can just see the pattern without using the function anymore. And then you just have to be careful. This is another parentheses around a -1. So this is going to oscillate between -1, +1, -1, +1. So for when we plug in 1, we're just getting 3 plus -1 is 2. Then what happens when I square the number? Now this would become +1. So 3 plus 1 would be 4. But when you cube it, you're going to be back to -1. So 3 and -1 would be back to 2. And then when you raise it to the 4th power, you're back to +1. So this is just going to oscillate between 2 and 4, 2 and 4. That's a pattern, right? 2, 4, 2, 4 is a predictable pattern. So that's what makes it a sequence. You can tell someone how to get the next term. And really, every odd term is 2 and every even term is 4. So you could even go out to the 100th term. You could either plug it into the function or just know the 100th term is even, it would be 4. All right, so see if you can list the first 4 terms of this sequence, and then we're going to graph it, and I'll show you how to just not connect the dots. So plug in 1, 2, 3, and 4 for n, and see what you get further numbers. So this is it. You're working with sequences. You're learning a new notation that you might not have known before, but it's not any harder than working with a function. So this would be 3 minus 2 is 1. And then 6 minus 2 would be 4. and then 9 minus 2 would be 7, and then 12 minus 2 would be 10. So I can see that there's a constant rate of change, right? Adding 3, adding 3, adding 3. So you're going to plot the point 1, comma 1, because that's kind of like your x value and your y value, 2, comma 4, 3, comma 7, and 4, comma 10 on your axis, but you're not going to connect the points. So 1, 1, 2, 4, 3, 7, and 4, 10. You can see that it's a linear function, but it's a linear sequence. So we're just not going to connect the points. And I mean, your brain knows it goes forever, but we don't have negative terms of a sequence. Sometimes sequences are better defined for applications in real life because, you know, if you're timing a liquid in a glass, there was not negative time, right? The liquid was in the glass and then you started the time. So you can't go backwards in time. Same thing with, like, you're not going to pay negative amounts of money for negative months in your apartment. All right, so here's something else. Writing out the nth term can be difficult, and I'm not going to have you do it too much, but this was the idea of figuring out what degree function you might have, like we did on the warm-up. And I was showing you that, hey, you can tell that this is a quadratic, not from a constant rate of change, but a constant after you do the first rate of change, the second rate of change is constant. So it's called finite differences, and what you do is you're just going to see what the difference is starting out. It might be linear right off the bat. This one's linear, right? Up by 5 each time. So that tells you that this is a linear function or an arithmetic sequence. So now on the next one, you're going to do it again, and it's not going to be constant. I'm going up by 3, then I'm going up by 4, then I'm going up by 5, then I'm going up by 6. So this was not linear. But the next level is increasing by the same amount each time. So because I went to the second level, this is a quadratic. Because this was constant after the first level, it's called a finite difference. First order finite difference. This is called first order finite difference. This is called second order finite difference. That was constant. This is a quadratic. On C, see if you can do it. You have to go down, I think, 3 levels, and then it becomes constant. So, you know, what are you adding each time? Do another level and do another level and see if it, you might need a calculator, see if it comes out constant. Harder to deal with when you need a further term. So that's when spreadsheets are useful because you can copy a pattern down in a spreadsheet, easier than kind of doing it in your head. So it says, how would this be written using a sub n or a sub k notation? They're using k because it's recursive, but you could still say a sub n. So the way you would write it is a sub k. How do I get the term I want? I take the term that comes before it, a sub k minus 1, and I add the term that came before that, a sub k minus 2. So this just tells you add the 2 preceding terms, and you need to tell the reader what a sub 1 is and what a sub 2 is in your example, because they don't know to start with 1 plus 1. So all this tells you is how to get the next term in a recursive sequence. You don't know that you're on term 8 or you're on term 11, but if you were on term 8, you would take term 6 and add term 7. So you don't actually plug numbers into the k's. A sub k just represents relevant order. So a sub k would come before a sub k plus 1. A sub k minus 1 would come before that. A sub k minus 2 would come before that. So if you were at a sub 15, this would be a sub 16, a sub 17, a sub 14, and a sub 13 would come before it. So if you wanted to get this term, you take the 2 terms that come before it. So whatever this is, if this was 7 and this was 13, you would add 7 plus 13 and get 20. You're not actually adding these numbers together, the 13, the 14, or the 15. And I think that's, when we start practicing recursive, I think that's what gets people caught up. So you read a recursive situation like a story. This says a sub 1 is 3. Great, so we know the first term of this sequence is 3. We need to find the next 3 terms in this pattern. How do I find the term? So to get a sub k plus 1, what do? We take the term that came before it and subtract 2, right? Because they're giving you this, and you want to find this. A sub k plus 1 is here, a sub k is here. So what would I do? Just subtract 2 from this 3. So 3 minus 2 would give me 1. How do I get the next term? I'm going to subtract 2 from the 1 and get negative 1. Then I'm going to subtract 2 again and get negative 3. So a recursive, you're not actually like plugging in like we did on the front page, plug in 5 and see what you get. You're taking the term that comes before it and doing some operation on it. So see if you can do example 3. How would you find the next 3 terms in that sequence? So you're starting at negative 3, 1, 2, 3 more terms past that. You're not plugging anything in. You're doing something to the previous term. It's called recursive. So what does it say to do? To get the term you want, just double the term that comes directly before it, right? 2 times a sub k minus 1. So what's the term that comes directly before it? Negative 3. All I have to do is double the negative 3. So now I'm at negative 6. Then I have to double the negative 6. So I'm at negative 12, then negative 24. So you could write a different function for this. So you could plug in term 100, or you could just double all the terms till you get to 100. Which one would be easier? Knowing the closed formula is easier. All right, factorials. People in stats, you've seen factorials this year. People that haven't taken stats might not recognize that this is an operation in mathematics. So all a factorial is the product of an integer and all the positive integers below it. So if I start with 3 factorial, that's 3 times 2 times 1, which equals 6. So the exclamation mark is actually a mathematical operation. And if you find it on your calculator, it's under the math key, but it's under probability at the top. So math probability, probability. See how it's choice number 4? So if I wanted to do, if I wanted to do 3 factorial, see how 3 factorial is 6? So let's just work backwards here. 2 factorial would just be 2 times 1, right? So that would just be 2. 1 factorial is just itself 1, and they define 0 factorial also as 1, just so the factorials don't kind of fall apart and all become zeros. Number 1, on the evaluate, there's an easy way to reduce this fraction so you don't have to use a calculator. So if you think about 11 factorial, that would be 11 times 10 times 9 times 8, all the way down to 1, right? But what's 10 factorial? Well, that just starts at 10 times 9 times 8, all the way down to 1. So won't all of these factors in common cancel, right? Because 11 factorial has 10 factorial in it. So isn't the answer just 11? So see if you can do these by reducing them first. I think number 2 you're going to have to use a calculator for, though, because you're going to be multiplying 20 times 19 times 18 times 17. So try doing 2 on a calculator. And when you type it in, you'll probably want to put the denominator 10 factorial, 8 factorial in one parentheses. And then try evaluating number 3. And actually, you could try 4 and 5, because now they're using a factorial in a sequence, and you're going to plug in 1, see what you get, plug in 2, see what you get, and plug in 3, see what you get. So see if you can finish 1 through 5. So it's under the math key and then prob number 4 exclamation mark. Math prob. There's no shortcut key. Is there, stats people? That's how you get to it, right? Well, if you know of a shortcut key, please share it, because I don't use factorial a lot, so if there's an easier way to get to that button. So for those first two, did you get, I don't know how many this is, 16 million? That one came out to 16 million? And this one came out to 6,720. All right, see if you can do 4 and 5. And then I might show you the Fibonacci video before we do guided practice.